All right, Raiders, this is our introduction to the chemical bonding unit. So in this overview, we're going to get just a taste of the concepts that we're going to be practicing in the unit. So get your notes ready. We're going to be taking our Cornell notes. So do make sure that you have space on your journal, on your paper or in your journal. We need to have a line down. Your red line on the paper is probably going to be about right here. You want to make a wider line than that to fit in main ideas, vocabulary. After your notes are completed, you may want to go back and write some quiz questions for yourself. And then on the right-hand side, we're going to be writing down our actual notes, the keywords, the ideas, repeated or stressed info. So if you hear me say things multiple times, you might want to write those phrases down. Formulas, diagrams, and pictures all go here on the right-hand side. When you're done taking your notes, it's a very good idea to do a summary, 3 to 5 sentences in your own words. It'll help the information stick if we do that. Okay, so first definitions to write down. This is the chemical bonding overview. That's what should go at the top of your notes for your title. Atoms are most stable with a filled valence shell, and we've done some practice already on looking at Bohr models and electron configurations to make sure that we have full shells. So there's two different ways that atoms can fill their shells. Atoms will either gain or lose electrons to become a more stable ion and then form ionic compounds, or they can share electrons in a covalent bond and form covalent compounds. So those are the two different types of bonds that we're going to be studying. So how do they form the ions? Let's look at that first. Let's look at ionic compounds. So if I have this set of Bohr models here, I have fluorine that I'm looking at the very top first. And fluorine has this electron configuration. All right, so this is the Bohr model. This is the electron configuration. It is in the second energy level, so it has two shells or levels, energy levels. There's two in the first energy level. They're paired in a S-shaped orbital. There's our 1s2. In our second energy level, we do have two that are paired in an S-shaped orbital as well. And then also within that second energy level, we have those peanut-shaped orbitals. So we have 1, 2, 3, 4, 5 electrons in that shell. So overall, in the whole shell, we have 7 electrons. And if we look at our electron configuration, that outer second energy level has 1, 2, plus 5 is 7 valence electrons. Well, what's going to be easier for fluorine to reach its octet? It's either going to be to push out the electrons in the outer energy level, or just add one in. And atoms are always going to do the thing that is least energy expensive. And it's easier to move one electron in than it is to try and push away the other outer 7 to get down to that smaller but full energy level. So that's what fluorine is going to do. Fluorine is going to add an electron. So instead of P5, it's going to be P6. And that gives it the octet. 2 plus 6 is now 8. There's our octet of 8 electrons. Sodium will also form an octet, but it's going to do it in a different way. If we look at sodium, this is its electron configuration right here. It is in the third energy level. So there are 3 shells. In the outer or third valence shell, there's only 1 valence electron. And we see that in the electron configuration also. So it has the same choice. It can either try and pull in 7 electrons to reach its octet, or if it just pushes away 1, there's a full energy level right here already. And that's the easiest thing for sodium to do. So that's really what it will do. It will push away 1, lose 1 electron. Okay, and that electron has a place it can go to over here too. So it's going to lose this outer energy level right here. So it now has only 2 energy levels, and it is stable with 8 electrons in its new valence shell. So the other thing that we see when we form these ions is that the symbol will change. The neutral atom for fluorine is just a capital F. But when we form an ion, it added a negative electron, which means it now has an extra -1 charge. So the formula for the fluoride ion is F-1. For sodium, we lost an electron. We still have those 11 positives, those 11 protons, but now we only have 10 electrons, right there. So it has a +1 charge left over, so its symbol is going to be the Na with the +1 charge. And here we remember that ionic bonds occur between metal and nonmetal ions. So in previous notes, we wrote down metals were on this side of the periodic table, nonmetals here. Metals will usually give away their electrons, whereas nonmetals will accept them. So we have these metallic cations and nonmetallic anions. And that's the way that we are going to name these two different ions. And we need to remember that. One thing that my students say helps them every year to remember the difference between cations and anions is this little mnemonic here, so you might as well write it down. The cation ions are positive. And, you know, it kind of gets to me, this cation ions. It's kind of a double redundancy on there, but it helps people remember. So if it helps you remember, then it works. Cation ions are positive. They're not cations or cautions, cations, and they are positively charged. All right, well then that means that the other thing is the anion, and that is negative. All right, so remember that anions are negative. A negative ion is an anion, and cations are positive with that T that kind of looks like a plus sign. All right, so that's how you tell the difference. Remember that as you write down the formulas, it's just the symbol for the element with the ionic charge in the upper right-hand corner. So cations are positive ions. They're going to be from metals. They're going to be losers of electrons. Anions, negative ions. They'll be the nonmetals, gainers of electrons. All right, so now to look at the study packet that we had in class. Right, we had this right here. We had this animation where you have sodium. It's a Lewis dot structure here. One valence electron, it's in group 1A. It loses that one electron, as we just saw, so it can form a more stable atom, which happens to be the sodium ion. Chloride does the opposite. It has 7 valence electrons. It wants 8, so it's going to gain an electron. When it gains that electron with a negative charge, it becomes a chloride ion. Well, now we have something interesting going on, because now we have things that are negatively charged, positively charged, and they are attracted to each other. And so you're going to want to pause this and make sure that you have this written down in your notes. This notation here, where we have the sodium atom, but then we have the plus on the outside of it. So that's telling us that we are missing the outer layer of electrons, and then we have a +1 charge. Here, this is showing us that this ion contained in the brackets here has that full octet, and it has a -1 charge. And these are attracted to each other, so we can write them as being stuck together like that. It's also kind of interesting to note that as they are opposites, they are still attracted to each other. So as we see mortal enemies here, cats and dogs. And the size difference is kind of interesting too. Sodium here, because it loses its outer shell, actually shrinks in size. It becomes a smaller substance. So cations are smaller than the atoms that they come from. Anions, on the other hand, because they gained electrons and electrons repel each other, they kind of spread out a little bit more. So they are bigger than the neutral atom that they came from. But those opposites attract. So even though they're completely different, they somehow manage to be stuck together. The second major type of bonds are those covalent bonds, and those are cooperative bonds where we have electrons being shared. Covalent bonds happen between two nonmetals, two or more nonmetals. So they're not ions forming. There's no giving up or accepting of electrons. They're sharing. And this tends to happen again when there's no metals, so no ionic bonds can form. And so here we have, for an example, two fluorine atoms. We can tell they're fluorine because they have atomic number of 9. They have 9 electrons there. And they don't have that full outer energy level, so they're not really happy. But they're right next to each other, and they each have a electron or an electron that is not paired, so they can share. And when they each share, now they're happy atoms. They're sharing valence electrons, and so when they share, included in this loop, it's kind of like they're holding hands. They have 1, 2, 3, 4, 5, 6, 7, 8 electrons here. And so this one now has, let's start with here, 1, 2, 3, 4, 5, 6, 7, 8 electrons. So they both have 8 electrons in their outer shell through the sharing of this bond right here. And we can actually write that. We're going to write this here because there is a shortcut way that they might write this occurring. And so with two fluorine atoms, each fluorine has 7 valence electrons. So that's 1, 2 for that S-shaped orbital, 3, 4, 5, 6, 7, and the same thing for this one. So what's going to happen is these are the ones that are going to pair up. And we can write that in a shorthand way by just writing F with a single line for that single bond and then the other F. All right, so another molecule, just for an example, if we are looking at this bonding right here, if we have one oxygen atom in the middle is what we have here, and then 2 hydrogen atoms on either side. And I know they're hydrogen because they each only have 1 electron, 1 electron. So that's got to be hydrogen. This has 6 electrons total, only 4 in the valence shell, so that's oxygen. 6 valence electrons, but it wants 8. So it can share 1 with this hydrogen and share 1 with this hydrogen. And in doing so, it now has its octet. So now we have 3 happy atoms because the oxygen now has 8, if we count, 1, 2, 3, 4, 5, 6, 7, 8, and each hydrogen now has 2. They're 1, and then 1 that they're sharing. 1, 2. And since hydrogen is such a small atom, 2 electrons will fill its valence shell, and so that's fine. It's stable. To draw the dot structure for this, we start with only 1 electron for each hydrogen. Oxygen is going to have 1, 2, 3, 4, 6, and the first 2 belong in that s orbital. 3, 4, 5, and then we'll just pair this up 6. And so this shows that we can pair these up here, and we can pair these right here. We can never have more than a pair of electrons together, but they definitely need to be paired in order to contribute to that full outer shell. And so if we're going to write that down in a shorthand way, we can just write O, H, and H. And those are our 2 different types of bonds, ionic and covalent bonds.